Hello there, and welcome back to Midnight Science. I'm so glad you found your way here tonight. Perhaps you're looking for something to help you unwind after a busy day. Or maybe you're simply drawn to the mysteries that hide in the darkest corners of space. Whatever brought you here, I hope you'll stay a while. You don't need to focus too hard or remember everything. Just settle in, let your shoulders drop, and allow your breathing to find its own gentle rhythm. Tonight, we're venturing into the realm of black holes. These aren't the frightening monsters of science fiction, but fascinating phenomena, cosmic sculptures carved by gravity itself. We'll explore them slowly and peacefully, wandering through ideas about time, light, gravity, and the curious boundaries where space curves back on itself. Some facts might spark your imagination. Others will simply wash over you like a calm wave. And if you find these quiet cosmic stories helpful as you drift towards sleep, a like or subscribe would mean the world. It helps other seekers of rest find this haven too. So take a deep breath, and when you're ready, let's begin our journey into the dark. Despite their name, black holes aren't empty voids or tunnels through space. They're regions where an enormous amount of mass has been compressed into an incredibly small area. This creates a gravitational pull so strong that nothing, not even light, can escape once it crosses a certain boundary. That boundary is called the event horizon. Inside, the mass continues to exist, collapsed down to what may be a point of infinite density, called a singularity. But from the outside, all we see is darkness, not because there's nothing there, but because the gravity is so intense that light itself is trapped. A black hole is less like a hole and more like a gravitational prison, where matter and energy go in but never come out. The event horizon is the defining feature of a black hole. It's the invisible boundary that marks the point where escape becomes impossible. Outside this boundary, you could still fire your rocket engines and move away. But once you cross it, all paths lead inward. No amount of thrust, no speed, not even light can turn back. The event horizon isn't a physical surface. There's no wall or membrane. It's simply the point where the curvature of space-time becomes so extreme that forward and backward lose their meaning. You wouldn't feel anything special crossing it, at least not right away. But you would have crossed a threshold into a region where time and space behave in ways our everyday experience can't prepare us for. It's a one-way door, silent and absolute. One of the strangest effects of a black hole's gravity is how it warps time. According to Einstein's theory of general relativity, the stronger the gravitational field, the slower time passes. Near a black hole, this effect becomes extreme. If you were to watch someone fall toward a black hole from a safe distance, you would see them slow down as they approach the event horizon. Their movements would become sluggish, their clocks would tick more slowly, and eventually they would appear to freeze in place, never quite crossing the boundary. From their perspective, however, time would feel normal. They would fall past the event horizon in finite time. This difference in the passage of time is called time dilation, and it's not just theory. It's a real, measurable effect of gravity's pull on the fabric of space-time itself. Not all stars become black holes. Only the most massive ones, typically those with more than about 20 times the mass of our Sun. have enough gravitational force to collapse into a black hole at the end of their lives. When such a star exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses inward in a fraction of a second, and if the remaining mass is great enough, it doesn't stop. It keeps collapsing, crushing past the density of a neutron star, past any known state of matter, until it forms a black hole. The outer layers of the star may explode outward in a supernova, but the core is gone, replaced by a region of spacetime so warped that nothing can escape. It's a transformation from light and heat into silence and darkness. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These giants contain millions, sometimes billions of times the mass of the Sun. They didn't form from a single collapsing star. Instead, they likely grew over time by consuming gas, dust, and even other black holes. The supermassive black hole at the center of the Milky Way is called Sagittarius A, and it has a mass of about 4 million suns. Despite this, it's relatively quiet, only occasionally feeding on nearby material. Some supermassive black holes are more active, surrounded by glowing disks of superheated gas that shine brighter than entire galaxies. These active cores are called quasars, and they can be seen across billions of light years. Even in the quietest galaxies, the central black hole remains, a gravitational anchor around which stars orbit. In 1974, physicist Stephen Hawking proposed something unexpected. Black holes, despite their reputation for consuming everything, can actually lose mass and eventually evaporate. This process, now called Hawking radiation, arises from quantum effects near the event horizon. In the vacuum of space, particle-antiparticle pairs constantly appear and disappear. Normally, they annihilate each other almost instantly. But near a black hole, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. Over time, this radiation carries away energy, and the black hole slowly shrinks. For a large black hole, this process takes an unimaginably long time, far longer than the current age of the universe. But for tiny black holes, if they exist, evaporation would happen much faster. Eventually, every black hole may fade into nothing, a quiet end to the universe's most extreme objects. If you were to fall feet first toward a black hole, the gravity pulling on your feet would be much stronger than the gravity pulling on your head. This difference in gravitational force is called a tidal force, and near a black hole, it becomes extreme. Your body would be stretched lengthwise and compressed from the sides, a process astrophysicists have whimsically named spaghettification. For smaller black holes, this stretching would begin long before you reach the event horizon, tearing you apart atom by atom. For supermassive black holes, the event horizon is so far from the center that tidal forces are initially gentler. You might cross the horizon without feeling anything unusual, only to be stretched apart deeper inside. Either way, the outcome is the same. The tidal forces near a black hole are not survivable. They are a quiet, inevitable consequence of gravity's grip. In 2015, scientists made a historic discovery. For the first time, they detected gravitational waves, ripples in the fabric of space-time caused by the collision of two black holes over 1 billion light-years away. These waves were predicted by Einstein over a century earlier, but they're incredibly faint. The two black holes, each about 30 times the mass of the Sun, spiraled into each other, merging in a fraction of a second. The collision released more energy than all the stars in the observable universe combined, but only in the form of gravitational waves. No light, no sound, just a shudder in space-time itself. Detectors on Earth picked up this signal as a brief chirp, a change in distance smaller than a proton. Since then, dozens more mergers have been detected, revealing a hidden population of black holes throughout the cosmos. These collisions are invisible to telescopes, but through gravitational waves, we can hear them. A common misconception is that black holes roam through space, vacuuming up everything nearby. In reality, black holes obey the same laws of gravity as any other massive object. If the Sun was suddenly replaced by a black hole of the same mass, Earth would continue orbiting exactly as it does now. The gravitational pull at Earth's distance wouldn't change. What makes black holes dangerous is proximity. If you get close enough to cross the event horizon, escape becomes impossible. But from a distance, a black hole's gravity is no different from that of a star or planet. Many black holes drift quietly through space, exerting their influence only on objects that venture too near. They don't hunt, they simply exist, patient and still, waiting for matter to fall in. At the very center of a black hole, according to general relativity, lies the singularity. This is a point where density becomes infinite and the curvature of space-time becomes infinitely steep. At the singularity, the equations that describe gravity and matter no longer make sense. They produce infinities and contradictions, signaling that our understanding is incomplete. Some physicists believe the singularity isn't a real physical object, but rather a sign that general relativity needs to be replaced by a deeper theory, one that incorporates quantum mechanics. Others think the singularity may be hidden behind the event horizon, forever out of reach. We may never know what truly happens there. The singularity remains one of the greatest mysteries in physics, a place where space, time, and matter converge into something we cannot yet describe. Black holes aren't just stationary objects. Many of them spin, and some spin extraordinarily fast. A spinning black hole is called a Kerr black hole, named after the physicist who first described them mathematically. The spin is a remnant of the angular momentum of the star that collapsed to form it. As the star's core shrinks, it spins faster and faster, like a figure skater pulling in their arms. A black hole can rotate at nearly the speed of light at its event horizon. This rotation drags space-time around with it, creating a region called the ergosphere, where nothing can remain still. Even light is pulled along by the spinning fabric of space. The faster a black hole spins, the more complex and strange the geometry around it becomes. These rotating giants are not just dark. They are whirling vortices in the structure of reality itself. Not all black holes are supermassive. Many are much smaller, with masses just a few times that of the Sun. These are called stellar mass black holes, and they form from the collapse of individual massive stars. Astronomers estimate that the Milky Way contains tens of millions of these black holes, scattered throughout the galaxy. Most of them are invisible, drifting alone through space with no nearby stars to illuminate them. Occasionally, one is found in a binary system, orbiting a companion star. In such cases, the black hole can pull gas from its companion, forming a glowing accretion disk that emits X-rays. These systems allow scientists to study black holes indirectly by observing how they affect their surroundings. But for every black hole we detect, there are likely thousands more, silent and unseen. For decades, black holes were only theoretical. We could detect their effects, but we couldn't see them directly. That changed in 2019, when the Event Horizon Telescope, a global network of radio observatories, released the first image of a black hole. The target was the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. The image shows a dark circular shadow surrounded by a bright ring of glowing gas. The shadow is the black hole's event horizon, the point beyond which no light escapes. The ring is the accretion disk, superheated material spiraling inward. The image was created by combining data from telescopes around the world, effectively turning the entire Earth into a single massive lens. It was a triumph of science and international collaboration, giving humanity its first direct glimpse of one of the universe's most mysterious objects. Though they seem eternal, black holes are not immortal. Through Hawking radiation, they slowly lose mass over time. For a black hole with the mass of the Sun, this evaporation process would take about 10 to the 67th power years, a number so large it's almost meaningless. But eventually, the black hole would shrink, and as it did, the process would accelerate. In its final moments, a black hole would radiate energy furiously, possibly ending in a burst of light and particles. By that time, the universe would be unimaginably old, and most stars would have burned out. The black holes themselves would be among the last surviving objects, glowing faintly in the darkness. And then, one by one, they would vanish, leaving behind only the memory of their existence, encoded in the faint radiation they emitted over eons. Some speculative theories suggest that the singularity at the center of a black hole might not be an end, but a beginning. In these models, the extreme conditions inside a black hole could trigger the formation of a new universe, budding off from our own in a way we cannot observe. This new universe would have its own space and time, completely disconnected from ours. If true, this would mean that black holes are not just destroyers, but creators. Every time a massive star collapses, it might give birth to a new cosmos, with its own stars, galaxies, and perhaps even life. We have no way to test this idea, and it remains firmly in the realm of speculation. But it's a beautiful thought that the darkest, most final-seeming objects in our universe might secretly be doorways to something new. For a long time, astronomers believed the closest known black hole was much farther. But in 2020, researchers identified a system called HR 6819, which appeared to contain a black hole just 1,000 light-years from Earth. Later studies have cast doubt on that claim, suggesting the system may not contain a black hole after all. Still, astronomers continue to search, and it's likely that black holes exist much closer than we've yet confirmed. There may even be rogue black holes, wandering through the galaxy alone, passing relatively near our solar system. But there's no need for concern. A black hole 1,000 light-years away poses no danger. Its gravity at that distance is negligible, no stronger than that of a distant star. These nearby black holes are simply neighbors, silent and invisible, drifting through the same galactic neighborhood we call home. Most black holes are thought to be electrically neutral, but in theory, a black hole could carry an electric charge. These are called Reissner-Nordstrom black holes, and they would have properties different from uncharged ones. A charged black hole would have two event horizons, an outer and an inner one, and the region between them would be bizarre and unstable. However, in practice, charged black holes are unlikely to exist for long. If a black hole had a net positive or negative charge, it would attract oppositely charged particles from the surrounding space, quickly neutralizing itself. So while charged black holes are mathematically possible, they are probably rare or short-lived in the real universe. Still, they remain a fascinating corner of black hole physics, a reminder that these objects can take many forms. Most black holes form from collapsing stars, but there's another possibility. In the chaotic, high-density conditions of the early universe, tiny regions of space might have been compressed enough to form black holes directly. These are called primordial black holes, and they could have a wide range of masses, from smaller than an atom to thousands of times the mass of the Sun. If they exist, primordial black holes might account for some of the universe's dark matter, the mysterious invisible substance that makes up most of the matter in the cosmos. So far, none have been definitively detected, but astronomers continue to search. These ancient black holes would be fossils from the first moments after the Big Bang, windows into a time when the universe was unimaginably hot and dense. Just as Earth orbits the Sun without falling into it, you could, in theory, orbit a black hole at a safe distance. As long as you stayed outside the event horizon and maintained enough speed, you would circle the black hole indefinitely. The closer you orbited, the faster you would need to move to avoid being pulled in. At the innermost stable circular orbit, you would be moving at a significant fraction of the speed of light. This orbit marks the edge of the region where stable paths are possible. Any closer, and you would spiral inward, unable to maintain your trajectory. These orbits are not just theoretical. Astronomers observe stars orbiting the supermassive black hole at the center of our galaxy, completing their circuits in just a few years. These stars move at thousands of kilometers per second, held in place by the black hole's immense gravity. When two black holes orbit each other, they gradually lose energy by emitting gravitational waves. As they spiral closer, the waves grow stronger, and the black holes accelerate. In the final moments before they merge, they orbit each other hundreds of times per second, moving at nearly the speed of light. When they collide, they don't bounce or explode. They merge smoothly, forming a single larger black hole. The collision releases a tremendous amount of energy, all in the form of gravitational waves that ripple across the universe. For a brief moment, the merger can emit more power than all the stars in the observable universe combined. But it does so silently, invisibly, detectable only through the subtle distortions it causes in spacetime. These mergers are some of the most energetic events in the cosmos, and we're only just beginning to study them. At a specific distance from a black hole, light itself can be bent into a circular path. This region is called the photon sphere. Here, photons, the particles of light, travel in closed loops around the black hole. They neither escape nor fall in. They simply orbit, trapped by the curvature of space-time. If you were somehow able to position yourself at the photon sphere and look to the side, you might see the back of your own head as light from you travels all the way around the black hole and returns. The photon sphere is unstable though. The slightest nudge would send the light either spiraling inward or escaping outward. It's a delicate, invisible shell around the black hole, a place where light dances on the edge of oblivion. When matter falls toward a black hole, it doesn't always disappear quietly. Some of it gets caught in the intense magnetic fields near the event horizon and is funneled into narrow jets that shoot outward at nearly the speed of light. These jets can extend for millions of light years, far beyond the host galaxy. They glow brightly in radio waves and are among the most energetic phenomena in the universe. Scientists aren't entirely sure how these jets form, but they seem to be powered by the rotational energy of the black hole itself. As the black hole spins, it drags magnetic field lines around with it, creating conditions that accelerate particles to incredible speeds. These jets can influence the evolution of the entire galaxies, heating gas, triggering or suppressing star formation, and shaping the large-scale structure of the cosmos. Around a spinning black hole, there's a region called the ergosphere, located just outside the event horizon. Within this zone, space-time itself is dragged around by the black hole's rotation. If you tried to hover in one place inside the ergosphere, you would fail. The rotation of space would pull you along, forcing you to move in the direction of the black hole's spin. You could still escape from the ergosphere, unlike from inside the event horizon, but you couldn't remain stationary. This dragging of space-time is called frame dragging, and it's one of the strangest predictions of general relativity. The ergosphere is a place where space doesn't just curve, it flows like a river, carrying everything with it. In space, no one can hear a black hole. There's no air or medium for sound waves to travel through, but the signals black holes produce, like gravitational waves, can be converted into audio frequencies that humans can hear. When LIGO detected the first black hole merger, scientists played back the signal as sound. It was a brief chirp, rising in pitch as the two black holes spiraled faster and faster, then ending abruptly as they merged. This sound isn't something you could hear in space. It's a translation, a way of making the invisible signals of gravity perceptible to human senses. Other black holes, particularly those feeding on nearby stars, emit X-rays that vary in intensity. These variations, too, can be turned into sound, creating eerie rhythms and pulses. In a sense, black holes have voices, and we're learning to listen. One of the biggest puzzles in black hole physics is the information paradox. According to quantum mechanics, information cannot be destroyed. But if something falls into a black hole and crosses the event horizon, that information seems to be lost forever. When the black hole eventually evaporates through Hawking radiation, where does the information go? Some physicists believe the information isn't truly lost. It might be encoded on the surface of the event horizon, in the Hawking radiation, or in subtle correlations that we don't yet understand. Others think the paradox reveals a flaw in our theories, pointing toward a deeper understanding of quantum gravity. The debate continues, but one thing is clear. Black holes challenge our most fundamental ideas about reality, forcing us to confront the limits of what we know. Most black holes fall into two categories: stellar mass black holes, with a few dozen times the sun's mass, and supermassive black holes, with millions or billions of solar masses. But what about black holes in between? These intermediate mass black holes, if they exist, would have masses ranging from hundreds to thousands of suns. They're harder to detect because they don't fit the usual patterns. They're too big to form from a single star and too small to sit at the centers of galaxies. Some candidates have been found, often in dense star clusters or colliding galaxies, but the evidence remains uncertain. If intermediate mass black holes are common, they might represent a missing link in the growth of supermassive black holes, seeds that formed early in the universe and grew over time. When we look at a black hole, we don't see the event horizon directly. We see its shadow, a dark region that's larger than the horizon itself. This happens because light passing near the black hole gets bent by its gravity. Some photons are bent so much that they spiral inward, never escaping. The boundary where this happens creates a dark silhouette against the glowing material around the black hole. For a non-rotating black hole, the shadow is about 2.6 times the size of the event horizon. For a spinning black hole, the shadow can be even larger and slightly distorted. This shadow is what the Event Horizon Telescope captured in 2019. It's not the black hole itself, but the fingerprint it leaves in the light around it. From the perspective of someone falling into a black hole, the experience would be unsettling but finite. You would cross the event horizon in a finite amount of proper time, the time measured by a clock you carry with you. But from the perspective of someone watching from far away, you would appear to slow down, redden, and fade, never quite crossing the horizon. This difference is due to time dilation. The closer you get to the event horizon, the more time dilates. To an outside observer, it takes infinite time for you to cross. But for you, falling in, time continues normally. You would pass the horizon, possibly without even noticing at first, and then continue falling toward the singularity. The universe outside would seem to speed up, aging rapidly as you plunged inward. It's a journey from which there is no return, but one that, from your perspective, ends all too quickly. When matter falls into a black hole, some of its mass is converted into energy. This process is far more efficient than nuclear fusion, the reaction that powers stars. In fusion, about 0.7% of the mass is converted to energy. But in the swirling disk around a black hole, up to 10% or even 40% of the mass can be turned into light and heat, depending on the black hole spin. This makes black holes the most efficient energy sources known. Quasars, the brightest objects in the universe, are powered by supermassive black holes consuming vast amounts of gas. A single quasar can outshine an entire galaxy of hundreds of billions of stars, all thanks to the incredible efficiency with which black holes extract energy from infalling matter. In the 1930s, before the term black hole was coined, physicists described these objects as frozen stars. The name referred to the way time dilation makes an object falling into a black hole appear to freeze at the event horizon from an outside perspective. In a sense, the name isn't entirely wrong. From our vantage point, anything crossing a black hole's event horizon seems to hang there forever, time slowed to a standstill. Modern physics tells us that the object does cross the horizon in its own time frame, but the outside universe never sees it happen. So in a way, black holes are frozen in time, at least from the perspective of distant observers. The name didn't stick, but it captures something true. To watch a black hole is to watch time itself slow and stop. At the heart of the galaxy, Messier 87, lies one of the most massive black holes ever discovered. It weighs about 6.6 billion times as much as our Sun and has an event horizon larger than our entire solar system. This is the same black hole that was imaged by the Event Horizon Telescope in 2019. But even it isn't the largest. In 2021, astronomers found evidence of a black hole in the galaxy TON 618 with an estimated mass of 66 billion suns. At that scale, the black hole's event horizon would stretch across hundreds of billions of kilometers. These ultramassive black holes are rare, but they exist, silent titans anchoring the centers of distant galaxies, remnants of a time when the universe was younger and more violent. The singularity at the center of a black hole is where general relativity predicts infinite density and curvature. But many physicists believe this is a sign that the theory is incomplete. When quantum mechanics is taken into account, the picture might change. At incredibly small scales, quantum effects might prevent matter from collapsing all the way to a point. Instead, the center of a black hole might be a region of incredibly dense but finite matter. Some theories suggest that quantum gravity could create a bounce, where collapsing matter reaches a minimum size and then expands again, possibly forming a new region of spacetime, or even a new universe. These ideas are speculative, but they hint at a future theory that unites gravity and quantum mechanics, one that might finally explain what lies at the heart of a black hole. Just as spacecraft use planets to gain speed in a gravitational slingshot maneuver, a black hole could do the same, but far more powerfully. If you approached a black hole at the right angle and speed, you could swing around it and be flung away at much higher velocity. For a spinning black hole, you could even extract some of its rotational energy through a process called the Penrose process. By carefully dropping an object into the ergosphere and letting it split, one piece falls in while the other escapes with more energy than it started with. This isn't science fiction. It's a real, predicted consequence of black hole physics. In theory, advanced civilizations could use black holes as cosmic power plants, extracting energy from their spin and using them to accelerate spacecraft to incredible speeds. Like massive galaxies and galaxy clusters, black holes can bend light through gravitational lensing. When a black hole passes between us and a distant star, the star's light curves around the black hole, creating multiple images or a bright ring. This effect, called microlensing, has been used to detect stellar mass black holes that would otherwise be invisible. The light doesn't pass through the black hole. Instead, it follows the curved space-time around it, like water flowing around a stone. These lensing events are brief, lasting days or weeks as the black hole drifts across our line of sight. But during that time, they reveal the presence of dark objects we could never see directly. Every gravitational lens is a reminder that light doesn't always travel in straight lines. Near massive objects, it follows the curves of space itself. When two black holes orbit each other, they form a binary system. If they're far apart, they can orbit for millions or even billions of years, slowly losing energy through gravitational waves. This process is called in spiral. The waves carry away orbital energy, causing the black holes to move closer together. At first, the effect is tiny, but as they draw nearer, the orbital period shortens and the gravitational waves grow stronger. The dance accelerates. Eventually, they reach the final moments, orbiting each other thousands of times per second before merging. These long, slow spirals are invisible to telescopes, but future gravitational wave detectors may be able to hear them years before the final collision. Two black holes, locked in an embrace that lasts eons, moving closer with every orbit until at last they become one. If black holes can have any mass, then theoretically, tiny black holes with the mass of a mountain or even smaller could exist. These micro black holes would evaporate almost immediately through Hawking radiation. A black hole with the mass of a car would vanish in less than a nanosecond, releasing a burst of energy. The smaller the black hole, the hotter and faster it evaporates. Some physicists have speculated that micro black holes might be created in high-energy particle collisions, such as those in the Large Hadron Collider. But even if they were, they would disappear so quickly they'd be harmless. These tiny black holes would never grow or consume matter. They would simply flash into existence and vanish, leaving only a faint trace in the particles they emit. Ghosts of gravity, gone before they could be seen. At the center of the Milky Way lies Sagittarius AI, our galaxy's supermassive black hole. Surrounding it are several stars in tight, fast orbits. The closest known star, called S2, or SVO2, completes a full orbit in just 16 years. At its closest approach, it comes within about 17 light hours of the black hole, moving at nearly 3% the speed of light. Astronomers have tracked this star for decades, watching it loop around the invisible mass at the galaxy's core. Its motion provides some of the best evidence for the black hole's existence. Each orbit is a test of Einstein's theory, and so far the predictions hold. S2 is a cosmic speedster, racing around a gravitational giant, bound by forces we can measure but never fully escape. The information paradox has puzzled physicists for decades. If a book falls into a black hole, what happens to the information in it? According to classical physics, it's lost forever. But quantum mechanics says information can't be destroyed. In recent years, some theorists have proposed that the information isn't lost. It's scrambled and encoded in the Hawking radiation the black hole emits. Recovering the information would be like trying to reconstruct a book from the smoke of a fire. Theoretically possible, but practically impossible. Others suggest the information might be stored on the event horizon itself, in a kind of holographic form. The debate continues, but the leading view is that black holes are not information destroyers. They're the universe's ultimate encryption machines, taking order and turning it into chaos, but never truly erasing it. If you could somehow survive crossing the event horizon of a supermassive black hole, you wouldn't hit a wall. You wouldn't feel a surface. The event horizon is a mathematical boundary, not a physical one. It's simply the point where escape velocity equals the speed of light. From your perspective falling inward, you might not even notice when you cross it. Space would look strange, light would be distorted, but there would be no sudden change. Only later, as tidal forces grew and space-time curved more sharply, would you realize that something had changed. You would try to turn around, to reverse course, but every direction would lead inward. The event horizon is a threshold of geometry, a place where the rules shift quietly and the way out disappears without a sound. If black holes are regions where nothing can escape, could there be regions where nothing can enter? These hypothetical objects are called white holes. In the mathematics of general relativity, White holes are the time reverse versions of black holes. While a black hole pulls everything inward, a white hole would push everything outward. Matter and light could emerge from a white hole, but nothing could fall in. However, white holes have never been observed, and most physicists believe they don't exist in nature. They may be mathematical curiosities, solutions to equations that don't correspond to real objects. Still, the idea persists. If black holes are the universe's sinks, could white holes be its fountains? And if so, where are they and what would they look like? For now, they remain ghosts in the equations, beautiful but elusive. In physics, no-hair theorem is the idea that black holes are simple. They can be described by just three properties: mass, spin, and electric charge. Everything else, all the details of the matter that fell in, is lost. The black hole has no hair, no distinguishing features. But recent theoretical work suggests this might not be entirely true. Quantum effects could give black holes a kind of soft hair, subtle information encoded near the event horizon that depends on what fell in. This wouldn't be visible in any ordinary sense, but it could help resolve the information paradox. If black holes have hair, even soft quantum hair, it means they're not as featureless as we thought. They might carry subtle traces of their past, written in the geometry of spacetime itself. This is one of the strangest predictions of relativity. As you fall toward a black hole, time outside appears to speed up due to time dilation. The closer you get to the event horizon, the faster the outside universe seems to age. If you could somehow look back as you cross the horizon, you might see stars flicker and die, galaxies collide, and billions of years pass in moments. In principle, you could witness the entire future of the cosmos unfold before your eyes. Of course, this is purely theoretical. The tidal forces would likely destroy you long before you could observe such a thing. And once you cross the horizon, looking back becomes impossible. But the mathematics allows for it, a window onto eternity, visible only to someone falling into oblivion. Most supermassive black holes are thought to spin in the same direction as their host galaxy. After all, they formed from the gas and stars that originally made up the galaxy. But some black holes spin in the opposite direction, a phenomenon called retrograde spin. This can happen if the black hole underwent a major merger with another black hole whose spin was misaligned, or if it accreted material from a chaotic or tilted disk. A retrograde black hole would have different jet properties and a differently shaped ergosphere. Its accretion disk might behave strangely, and the energy extraction through frame dragging would be affected. These backward spinning giants are reminders that black holes have histories shaped by collisions, captures, and the turbulent flows of cosmic gas. In science fiction, black holes are often portrayed as portals or wormholes, shortcuts through space and time. In reality, the mathematics of general relativity does allow for solutions called Einstein-Rosen bridges, or wormholes, that connect two distant regions of spacetime. A black hole could, in theory, be one end of such a bridge. But there's a catch. These wormholes are unstable. They would collapse almost instantly, long before anything could pass through. Even if you could keep one open, the tidal forces inside would be lethal. And most physicists believe that real black holes don't contain traversable wormholes. They're dead ends, not doorways. Still, the possibility lingers in the equations. a tantalizing hint that space-time might be more connected than it seems. For most of history, astronomy was about seeing light, but gravitational waves have opened a new sense, a way to hear the universe. When black holes merge, they don't emit light. They emit ripples in space-time, and those ripples carry sound of a sort. By converting the frequency of gravitational waves into audio, scientists have created soundscapes of cosmic collisions. The mergers sound like chirps, rising in pitch and volume, then ending abruptly. Each chirp is unique, depending on the masses and spins of the black holes involved. Some are high and quick, others low and drawn out. Together, they form a symphony of gravity, a concert playing across the cosmos, audible only to the detectors that listen for the trembling of space itself. Given their reputation, you might expect black holes to be loud, violent places, but in reality, they're remarkably quiet. There's no air in space to carry sound, and the processes that occur around black holes, accretion, jets, even the event horizon itself, are largely silent. The gravitational waves they emit are inaudible without special instruments. The light from their accretion disks can be bright, but it's often absorbed or scattered before reaching us. Many black holes are invisible, detectable only through their gravitational effects. They don't roar or scream. They simply exist, pulling, bending, and shaping the space around them with a kind of silent authority. In a universe full of noise, black holes are the quiet centers, places where even sound cannot survive. In the crowded cores of globular clusters, where thousands of stars are packed into a small volume, conditions might be right for intermediate mass black holes to form. Stars could collide and merge, building up a massive object over time, or several stellar mass black holes could sink to the center and merge together. These processes could create black holes with hundreds or thousands of solar masses. Some globular clusters show signs of harboring such objects, stars moving in ways that suggest a massive, unseen presence at the center. But confirming these black holes is difficult. They're too small to have the bright accretion disks of supermassive black holes, and too large to form through normal stellar collapse. They occupy a middle ground, elusive and rare. By definition, nothing can escape from inside a black hole's event horizon, not even light. This is why they're called black. But the region around a black hole can be incredibly bright. As gas spirals inward, friction heats it to millions of degrees, causing it to glow in X-rays and other wavelengths. The black hole itself remains dark, but its surroundings can outshine entire galaxies. This contrast is part of what makes black holes so striking. At the center of all that brilliance is pure darkness, a void that emits nothing. It's like a shadow cast by gravity, a silhouette against the glowing chaos of infalling matter. The idea of an object so dense that light cannot escape was first proposed in the late 18th century, but it was mostly forgotten. The modern concept of black holes emerged from Einstein's general relativity in 1915. Carl Schwarzschild found the first exact solution in 1916, describing what we now call a non-rotating black hole. But for decades, these solutions were considered mathematical curiosities, not real objects. It wasn't until the 1960s, with the discovery of quasars and neutron stars, that physicists began to take black holes seriously. The term black hole itself was coined by John Wheeler in 1967. Since then, the field has exploded. We've detected them, imaged them, and heard them collide. In less than a century, Black holes have gone from theory to reality, from speculation to science. While black holes can consume matter, they don't do so quickly. A supermassive black hole at the center of a galaxy might accrete only a few solar masses per year, sometimes less. Over millions of years this adds up, but on human timescales, the growth is imperceptible. Even a stellar mass black hole in a binary system, actively feeding on a companion star, might take thousands of years to double its mass. Black holes are patient. They don't rush. They simply wait for matter to fall within their reach, and when it does, they draw it in slowly, methodically, adding to their mass one atom at a time. In a universe that operates on timescales of billions of years, black holes have all the time they need. In 1969, physicist Roger Penrose described a way to extract energy from a rotating black hole. The idea involves dropping an object into the ergosphere, the region where spacetime is dragged around by the black hole's spin. Inside the ergosphere, the object splits into two pieces. One piece falls into the black hole, while the other escapes, carrying away more energy than the original object had. The extra energy comes from the black hole's rotation, slowing it down slightly. This process could, in theory, be used by advanced civilizations to power their technology. A spinning black hole could serve as a cosmic battery, providing energy for billions of years until its spin is exhausted. The Penrose process is real physics, a strange consequence of rotating space-time and the interplay between mass and motion. If black hole formed in the first moments after the Big Bang, they would be older than any star, older than any galaxy. These primordial black holes could have a wide range of masses, and if they're small enough, they might be evaporating right now through Hawking radiation. Larger primordial black holes could still exist, drifting through space, invisible and ancient. Some scientists think these objects could make up part or all of the dark matter in the universe. If so, the invisible mass that shapes galaxies and holds clusters together might not be exotic particles, but black holes formed when the universe was less than a second old. It's a compelling idea, though not yet proven. If true, it would mean that black holes are not just the endpoints of stellar evolution. They're also relics of creation itself. Around a black hole, there's a limit to how close an object can orbit and remain stable. This boundary is called the innermost stable circular orbit, or ISCO. Inside this orbit, any object will spiral inward and fall into the black hole. For a non-rotating black hole, the ISCO is at 3 times the radius of the event horizon. For a rapidly spinning black hole, it can be much closer, almost at the horizon itself. The ISCO marks the inner edge of the accretion disk, the swirling ring of hot gas and dust around the black hole. Inside this boundary, the material moves faster and faster, heating up and emitting intense radiation before finally disappearing. The ISCO is the last point of stability, the final orbit before the fall. In the hot, dense conditions just after the Big Bang, regions of space that were slightly denser than their surroundings might have collapsed directly into black holes. These primordial black holes wouldn't need stars to form them. They could exist at any mass, from incredibly tiny to thousands of solar masses. If they're common, they might explain some astronomical mysteries, like the rapid growth of supermassive black holes in the early universe, or the nature of dark matter. But detecting primordial black holes is difficult. They don't emit light, and if they're small, they might have already evaporated. Still, the search continues. Finding even one primordial black hole would confirm that these objects can form without stars, and that the universe's first moments were even stranger than we imagine. In the mathematics of general relativity, it's possible for a singularity to exist without an event horizon, a so-called naked singularity. Such an object would be visible from the outside, and its effects would be unshielded by the protective cloak of a black hole. But physicist Roger Penrose proposed the cosmic censorship hypothesis, which suggests that naked singularities cannot exist in nature. Every singularity must be hidden behind an event horizon. So far, this hypothesis seems to hold. We've never observed a naked singularity, and most physicists believe they're impossible. If cosmic censorship is true, it means the universe has a kind of modesty, hiding its most extreme singular points from view. The singularity is not just unreachable, it's invisible, wrapped in darkness, forever out of sight. One of the biggest mysteries in astrophysics is how supermassive black holes got so big so fast. Astronomers have found black holes with billions of solar masses that existed when the universe was less than 1 billion years old. That's not enough time for them to grow from stellar mass black holes by accretion alone. Several theories try to explain this. Perhaps they formed from the direct collapse of massive gas clouds, skipping the star phase entirely. Or maybe they grew through rapid mergers in dense environments. Another possibility is that they started as intermediate mass black holes, seeds that formed early and grew quickly. Whatever the explanation, these ancient giants tell us that black holes were shaping galaxies from the very beginning, influencing the cosmos long before most stars had even formed. According to Hawking's calculations, black holes have a temperature, but it's incredibly low. The temperature of a black hole is inversely proportional to its mass. A stellar mass black hole has a temperature of only a few billionths of a degree above absolute zero, colder than the cosmic microwave background. For a supermassive black hole, the temperature is even lower, far too cold to emit any meaningful radiation. Only the smallest black holes, if they exist, would have high temperatures and emit significant Hawking radiation. As a black hole evaporates and loses mass, its temperature rises and irradiates faster. In its final moments, a black hole becomes incredibly hot, possibly ending in a brief flash of light. But for the black holes we observe today, their temperature is so low they're effectively frozen, colder than the space around them. There's growing evidence that supermassive black holes and their host galaxies evolve together. The mass of a galaxy's central black hole is closely related to the mass of the galaxy's bulge, the dense central region of stars. This suggests that black holes don't just sit passively at galactic centers. They influence the formation and evolution of galaxies themselves. Jets and winds from black holes can heat or expel gas, regulating star formation. They can trigger bursts of star birth or shut it down entirely. In the early universe, the first black holes might have helped shape the first galaxies, acting as gravitational anchors and energy sources. Black holes are not just passengers in the cosmic story. They're architects shaping the structures that surround them. Once you cross the event horizon, there's no going back. Every possible path you could take, no matter how you fire your rockets or how fast you move, leads inward toward the singularity. In a sense, The future direction in space becomes the direction toward the center. You're not just unable to escape, you're unable to even move away. The geometry of space-time inside the event horizon is so warped that outward ceases to have meaning. This is what makes black holes truly inescapable. It's not just that the gravity is strong, it's that the structure of space and time itself has been reshaped. Falling into a black hole is like falling into the future, a future that has only one destination and no way to turn around. More than any other object, black holes push the boundaries of physics. They sit at the intersection of quantum mechanics and general relativity, two theories that describe the universe with extraordinary accuracy, but which are fundamentally incompatible. At the singularity, both theories break down. General relativity predicts infinite curvature. Quantum mechanics says nothing can truly be localized to a point. The result is a contradiction, a place where our best theories fail. Solving this problem requires a theory of quantum gravity, something physicists have been working toward for decades. Black holes are not just objects to study, they're laboratories, places where the universe reveals the limits of our knowledge. And in those limits, we may find the key to understanding reality itself. Though black holes can be described by just a few properties, mass, spin, and charge, each one has a story. Some formed from the collapse of a single star, inheriting its rotation and magnetic field. Others grew through mergers, combining the spins and masses of multiple black holes in violent collisions. Supermassive black holes at the centers of galaxies have consumed countless stars, gas clouds, and smaller black holes, each meal adding to their mass and spin. Some have been quiet for billions of years. Others are actively feeding, surrounded by glowing disks and powerful jets. Though they may look similar from the outside, each black hole carries within it the history of everything it has consumed, written in the geometry of space-time, silent and unchanging. The event horizon is not a physical surface, but a light surface. It's the boundary where light, traveling at its maximum speed, can only just barely stay in place. Outside this boundary, light can escape, though it requires more and more energy to do so the closer you get. At the boundary itself, light moves in circles, trapped but not falling. Inside, even light is pulled inexorably inward. The event horizon is defined not by matter or energy, but by the paths that light can take. In a sense, the black hole is a region where the universe's speed limit, the speed of light, is no longer fast enough. It's a place where even the fastest thing in the cosmos cannot outrun gravity. When we think about black holes, we're confronting objects of such immense scale and power that they dwarf everything we know. A single supermassive black hole can contain the mass of billions of suns. Its event horizon can stretch for billions of kilometers. It warps space-time so profoundly that time itself slows near it. These are forces and scale beyond human experience, beyond imagination, yet we can study them. We can detect them, measure them, and even, in a sense, see them. In doing so, we glimpse something vast and ancient, something that reminds us that we are small, fleeting, and part of a universe far stranger and larger than we can ever fully comprehend. And perhaps that's the most relaxing thought of all, that the universe holds mysteries so deep, we'll never run out of things to wonder about. And so, our quiet journey through the darkest objects in the universe comes to a gentle close. We've drifted together through event horizons, singularities, and the strange geometry of spacetime. From colliding giants to the slow evaporation of Hawking radiation, we've explored the quiet mysteries of black holes, one sleepy fact at a time. If your eyes are already heavy, that's just fine. Let the last traces of these cosmic wonders fade gently behind your thoughts, and let your breath carry you softly into rest. There's still so much more to discover, so many more mysteries waiting in the darkness. But for now, you've learned enough. You've traveled far, to the edges of light and time, and the universe can wait until morning. Black holes are not monsters. They're not destroyers. They're simply part of the universe's quiet architecture, patient and still, waiting in the dark. And perhaps that's the most peaceful thought of all, that even in the darkest places, there is structure, there is beauty, there is stillness. Thank you for spending this time with me, floating through the mysteries of gravity and light. May your dreams tonight be gentle. May your body rest like starlight and water. And may you carry with you, even faintly, the memory of a universe that holds both light and darkness, both questions and silence. If you happen to still be awake, you can go ahead and explore more cosmic wonders in the next video. And if you'd like to drift off to more stories like this, softly told, filled with wonder, consider subscribing. There's always more to explore, one sleepy soul at a time. Good night.